Hey guys, as part of the roads upgrade and pavement engineering class, today I'm continuing chapter 5 for asphalt pavement. And we are at part 4, nail thickness design. Basically, we'll discuss how the nail thickness was determined. In detail, we will talk about the general procedures, design index, followed by one simple example. In terms of general design procedures, first we have to collect and analyze the traffic data and determine the corresponding traffic level. Then we will need to determine the subgrade resilient modulus based on the soil type and the underground water table. If it is below the required value, we'll have to improve the highway subgrade through various appropriate methods. Next, we will collect the local pavement structure combination and material property requirements. Then we can move on to propose the pavement structure combination. Once we have the pavement structures, the design index can be selected. Meanwhile, design parameters like layer modulus can be determined. In addition, for performance control, CBR values of graduated materials, the unconfined compressive strength of inorganic binder stabilized materials, the low temperature requirements of asphalt binder, failure strain at low temperature, dynamic stability, penetration strength, and wall stability of asphalt mixture also needs to be checked. In addition, we have to determine the temperature adjustment coefficient or equivalent temperature based on the local temperature. Due to the temperature differences between asphalt mixture in the field and asphalt mixture and standard laboratory testing conditions, we have to determine the temperature adjustment coefficient or equivalent temperature. After all the design data were collected, the stress response required for the design index calculation can be calculated using multi-elastic layer theory. Finally, the design index of proposed pavement structures need to be checked for acceptance. Otherwise, the pavement structure has to be adjusted. In terms of design index, different pavement layer combinations will require different specific design index. For pavement structure with a semi-rigid base layer, the design index are tensile stress at the bottom of base layer and the permanent deformation of surface layer. It indicates that the fatigue life of the semi-rigid base layer has to be larger than the corresponding accumulated equivalent single axial loading, while the permanent deformation of asphalt surface layer has to be lower than the corresponding requirement in the specification. For other pavement structures, different design index have to be checked. For pavement structure with a semi-rigid base layer, the tensile stress of base layer needed for fatigue life calculation is at the bottom of the base layer, but in the direction of traffic direction. The compressive stress used for permanent deformation calculation is located on top of each sublayer of the asphalt layer, and the mechanical response at the 4 locations A, B, C, and D all have to be checked, and the maximum value will be used for later calculation. Next, we will take a look at an example. The project background is like this. An expressway in northern part of China with design speed 100 km/h and design life 15 years. The national zone belongs to 2.2, and the asphalt pavement climatic zone is also 2.2 with annual rainfall 607 millimeters. The average annual temperature is 11.6 degrees Celsius. In terms of traffic data, with 15 years design life, 3,500 per day traffic volume, 6.5% increase rate, 0.55 direction factor, 0.5 lane distribution factor. The accumulated traffic volume in 15 years is 8.5 million, which can be classified as heavy traffic. Based on the local experience and the specification requirements, material availability, construction conditions, the pavement structure as shown in this table was proposed. Since the proposed pavement structure has a semi-rigid base layer, the two design indexes are tensile stress at the bottom of the base layer and permanent deformation of the asphalt mixture layer. The fatigue life of asphalt mixture NF2 should be higher than the corresponding accumulated equivalent single axial loading. Based on the calculation, NF2 is equal to 1.57 times 10 to the power 9, which is larger than the equivalent single axial loading, which is 1.51 times 10 to the power 9. For permanent deformation calculation, the design layer was divided into 7 sublayers. The permanent deformation of each sublayer was first checked, which was transferred from the laboratory writing depth data of asphalt mixture. The total permanent deformation was determined to be 14.584 millimeter, which was less than the maximum allowable value, which is 15.0 millimeter. Low temperature cracking resistance of asphalt mixture was also verified. As we can see here, the proposed pavement structure meets the design requirements. Alright guys, that's all for my lectures on asphalt pavement design. Thank you.